to design a filter and to read the data and then to do data processing. But it's the time because when you write a report, maybe you need some knowledge to finish your report. So you know the assignment one is basically have two parts. One is the report. A report is a group report. That means one group only write one report. So in the first assignment, it is for a group based. So that means every members get a similar mark if there's no distribution. Like if all the people I assume is contributed evenly. But we have another part is called prioritization, because next week the prioritization will be cannot be run even by Zoom. Because it's holiday, so I show you in the I mean maybe you have already noticed the announcement. I think like in the home page I put this hello, can you hear me?
Yeah.
Can you see the things? No, you cannot see, right?
No.
We will share. I will share the screen. Uh, this time share the screen. So you know like because of the coronavirus outbreak, so we extend our teaching in with 1 week, and then another is like we change the assessment. So this is a formal approved. Before we thought like we will only give the pass or fail, but the UTS not agree. So that means like we still give you a mark, but we change the percentage. We remove the final exam because final exam difficult to run uh, remotely. So we remove the final exam, but the rest we will still count the marks. So in that case, uh, basically like all of the mark is from the project. I know like some other university they only count the pass or fail, but maybe UTS we haven't do like that. But we look at the change. So so the change for the how to pass the subject, you have three stage. You need to get overall 50 marks or more to pass the subject. The first assignment is due next week, next Tuesday. I put next Tuesday because next Monday is holiday. I make next Tuesday 6 p.m. Uh, you can see that we will ask you to submit to the Converse online and sorry on time in the Converse. We will show you. Due to the Easter holiday, stage one demonstration is replaced by a 2 to 8 minutes video clip. So this one will also to be submitted online. Every member of the group must be part of the video clip in some way. That means you either appearing in it or narrating some content. So there's no other changes. So this is the stage one. Do you have any problem with the stage one? It's due next week. The project report is a group report, and the video is also you made a video, but maybe everyone will appear in the video. And you know, like there's a detailed requirements for the report, and I agree that maybe Jeffrey or Carrie will discuss with you during the lab time. What's our requirements? Yeah, Carrie already said that. So now we look at this is for stage two. Stage one and stage two, we have you know like the percentage change to 25%. You know before is 15% for stage one, and stage two is increased to 30%. And stage two is basically the report is not individual report, but it's group report. But when you write a report, you need to mark which part is who finished this part. We will base on that to give individual mark, and also the presentation, the demonstration is use the Zoom to demo. It's not use video. But for the assignment 3, we need to build a 15-minute video as well, and also we have project report. Assignment 3 is 45%. It's the most of the percentage in the stage 3. So stage 3 is quite challenging because we cannot use hardware, and we will find the best way to run this one, and we will discuss with you maybe later. But now is this is the change of the assessment. I know this is a very big change. If you have any question, will you please let me know. If really this have a difficulty, we can still negotiable for the assignment. But this one is currently approved version. Unless you have some very urgent request, you just like this one will be the final if no other urgent request. So this is the changing about assessment. So next week, because it's a holiday, you just submit the assignment 1 online. Now we continue our discussion. So last week we continue discussion. We go to Zoom Canvas. We go to the lecture 3. We look at what we should still study. So lecture 3. So last week I discussed with you step response matching method to design IIR filter. So first I want to give you maybe we do a survey to whether you learn well or not. So what's the difference between IIR filter and the FIR filter? Maybe I put a survey. So you can respond to the survey, the polls now to let us see. I give you a, you can see there's a question, there's a filter. Can you tell me this is IIR filter or FIR filter? Another minute left. Before we tell the result, we look at what is IIR filter, what's FIR filter. So we look at here. So
There are
this
two
video.
different types of filters that are used in digital signal processing. One is called FIR and the other is called IIR. We're going to explain IIR is an acronym that's simply as a sum of weighted values of the past input.
So this is a FIR filter. So this FIR filter, this side, right-hand side is IIR filter. You can the major difference is in the right-hand side. For the FIR, it's only have input item, so they only have a BK. But for the IIR, so you have a feedback term in the right-hand side. That means YN minus YN minus K appears. So in that case, so our question, I think, is this FIR or IIR? You still have a minute to vote. So 11 students select FIR. I think this is a correct answer. So this is a FIR filter. because you can see there's no y item, yn item in the right hand side. So you can see you compare with this one. So this one is similar with this one, right? This summation of just only input. So for this one, y is not IIR because here IIR should have a output in the right hand side, but no output in the right hand side. So that's the first polling. So I under this one. I think most students get the right answer. So I think this is FIR, the structure FIR and IIR. When you design FIR or IIR filter, you mainly need to design first you need to determine the order. That means the M. You can see here the M. What's the order of the filter? Because the order of the filter is very important. The performance of the filter is mainly, I mean, not mainly, it's greatly influenced by the order. Because the higher order, you can normally design a accurate, uh, mm, higher accurate filter. So now last week we discussed the IR filter design as IR filter design. So we design both AK and BK, but we use impulse response matching method. But now we discuss it by using another important method called uh, bilinear transformation. Have you heard about bilinear transformation? So we go to bilinear transformation method. Actually, I put some reading material, and for example, this one have a IIR filter uh, design. Is this for this one is I think is I read it's in the later because the web is a little bit slow. I prepared one myself. Uh, First is what's the how to derive the bilinear transformation. How can how does it comes? For example, the structure finally is like this. It's something like this, right? It's S is equals to 2 over Ts. Ts is the sampling time. Here is an error times z minus 1 divided by z plus 1. This is the z transform. Actually, this is the bilinear transformation. Actually, this bilinear transformation can be also treated as a response equivalent method or response approximation method, because for the we approximate integration. Because for the continuous time, if I have integration, it's actually yt equals to integrate from 0 to t of the input, right? You got y output. For the discrete time, we want to find the equivalent, or not fully equivalent here, is approximately equivalent, uh, equivalent HD. That means digital system. That this one is also integration. That means YK is the integration, approximate integration of input, and then we can use trapezoidal approximation to build YK. For example, YK is the output of integration. So the previous integration plus this previous integration. Integration is the area of here, right? And the previous integration plus the current value here, the area. So this area, if we use trapezoidal approximation, and then we can use this line plus this line times the sampling time. That means xk plus xk minus 1, and times the ts is the this length, and then the area need divided by half, and then we can get yk equals yk minus 1 plus ts times this, and based on that we can do z transform, and we can get yz divided by xz. Similar as the in step response matching method, we only calculate yz and dz and the xz the relationship, and we can get the approximation of integration in the digital system, discrete time system, and then this integration in the continuous time is equivalent as 1 over s. So in that case, we make them equivalent, approximately equal, and then we get the 1 over s is equal to this one, and we opposite it, and we can get the bilinear transformation. And then the bilinear transformation is quite easy, right? If you give me a continuous filter, and I just use, because continuous filter, you have the Laplace transform operator s, and then you just change the s as 2 over ts 1 minus z minus 1 divided by 1 plus z minus 1, and then you submit in the trans function, and then you can get exactly the digital system. This use bilinear transformation. So this is how does it comes? Actually, the mainly is we want to equivalent, use the equivalence method. Now we go to we continue with our discussion here. So here have a detailed explanation about bilinear transformation. My computer is a bit slow, but I. So this is the bilinear transformation we derived. So this is just like approximation of integration, and then you can get this one. They give an example how to design the. They have design example how to design these things, but I also can read. I also give you some reading material. I mean some video. Some video here. You can they discuss about use bilinear transformation. But there's one thing I want to emphasize is like bilinear transformation is good in the sense like it is no frequency overlap called aliasing. But the bad thing is like it have a frequency ramp. That means the discrete time frequency and the continuous time frequency, they are not linearly related. They have a ramping. Yep. So the ramping one, they have the discussion here. This one very clear tell you.
So after our messy introduction here, let's limited range. So how does it look like?
This is the one, the ramping
so we can
formulation.
pi,
so we can see
and then there's
this
the
is a very clear explanation
same
here.
idea here.
Because we don't have enough time to
so
go
this
detail,
means that this formula
we can I leave you to have read.
Proportional to omega for.
So why is the one thing? Because like in the digital system, there's if you normalize the frequency, you know how to normalize the frequency, because if your sampling rate is a fixed value sampling rate, and then your filter can only sense the half of the sampling rate. right? This is called Nyquist theorem. So in that case, you normally assume like the Nyquist sampling rate, or your half of your sampling rate is the highest frequency. So and the lowest frequency is half of the minus half. So in that case, but your analog filter, the frequency is from 0 to infinite. So that's why you cannot linearly match each other, right? Map each other. You can see this is from minus pi to positive pi. This corresponding to radians, because for the frequency is hertz. If in hertz is minus positive half and minus half hertz. But for the if it's radians, it's minus pi. It's minus pi to positive pi. But you can you need to match to all the frequencies. So they are ramping. So in that case, when you design a filter, they have here have an example, a very good example here.
This is filter design example number 1. Design a Butterworth low-pass filter using the bilinear transform. Let's walk through a general approach to the design and evaluation of this discrete time Butterworth low-pass filter. Specs include 44.1 kHz system sampling frequency, 5 kHz passband edge.
So here, give you a question, let you to design a low-pass Butterworth filter. This will give you a very detailed explanation. But unfortunately, here the bilinear transformation is a little bit different with the one we discussed. So they are using a different formula. I will show you later, but they are very similar. But actually, the design procedure is exactly the same. First, we need to, based on the digital filter requirements, we ramping back to the analog filter, and then we design we based on the requirement in the analog filter design, we design the analog filter first. So the first very difficult part is how to determine the order of the filter. There's a formula, but because this subject we can use MATLAB to design the filter. Because the higher order you can design. So we didn't emphasize. But if you are really interested, there's lots of book. If you read a book, if you read any book, they will teach you how to calculate the order of the frequency of the filter. So we look at where they designed. So this is the procedure, and then this is the design. They determine the order. So this is the first. They need to map the analog filter, digital filter to analog filter. So in that case, when you design a filter, you have a pass band and a stop band. So basically, that's because of the nature of the filter. You cannot design called ideal filter. The ideal filter means like in the pass band, there's no ripple, and in the stop band there is no ripple as well, and then there's in the transition band there's a very sharp. It's not possible because all the filter, if you design at least in the linear filter, you cannot implement. So in that case, you give some tolerance, and here this you have a pass band and the stop band. The so let me. So sorry, everyone. Can everyone hear me?
Yeah.
Yeah, good. So here, this example is quite a useful example. You can see they first do the things, and then they calculate the order, determine the filter order. So it's based on the ripple and pass band and stop band requirement. They use formula, and then this is for Butterworth filter. I remember in the first lecture I show you there's a in the in the in the analog field design, I use hardware. I using MATLAB to design the filter. They can automatically tell you the order. Actually, they are based on the formula similar like this. So they can calculate and then calculate the order of the system, of the filter, and then they design the Butterworth. This is the Butterworth filter. This fourth order. They determine the n is fourth order is enough, and then they just design fourth order. Of course, if you use a high order, still can satisfy the design requirements, but will waste of your resources. So this is the fourth order, and then we need to discretize. Use just simply use S replaced by this. You can see this code also called bilinear transformation, but you can see this is a little different with bilinear transformation. Can you tell the difference? The real one is 2 over TS, right? Here no 2 over TS, but sometimes they still use, some people they use this value is still okay. So they use MAPL to calculate. Finally, they calculate.
And by keying in as my original input the h of s that I just found earlier, and incidentally the blue printout here is the result of MAPL calculation of each step. Next, I'll evaluate h of s at this specific frequency. And just to confirm, it looks like we have nice.
So you can see this one, and then the most important thing here also have something. This is very annoying. Yeah. So you can see we can still this calculate the. This is the Z transform. After Z transform, you can get the bilinear, get a digital filter using bilinear transformation, and then they calculate the spectrum of the designed. The spectrum is that this is spectrum is a low pass, really low pass, and then they also finally they discuss what I want you to see. Like you read this video, they tell you how to use live view to check your design. So I think live view have provided you how to design the Butterworth filter things. So I think here, and also here I have a zero pole plot is very important as well. So this is I discuss, I give you, and also some video to emphasize how to design the IIR filter by using bilinear transformation. Basically, this kind of designs are all very traditional design method, use from analog first and then transfer to digital. So I will not discuss too much about here, but first and next we will discuss FIR filter. FIR filter, why we will already have a IIR filter, why we should design FIR filter? Of course, they must have some advantage. So what's the advantage of FIR filter? Maybe we look at here, this video, in the end of this video, they discussed the advantage and the disadvantage. You can see for the.
And you're interested in a frequency selective or bandpass high.
So for the FIR filter, they can use optimization method to design. That means I would, if you are interested, actually they have lots of, they can even use in the time domain, they use a system identification method to design a FIR filter. That means, for example, if you have a filter, you know the impulse response, the continuous impulse response, and then you use optimization method, you can design an equivalent digital filter to design matching with that. And also you can have a arbitrary magnitude phase response. So that means they have more freedom, but the order will be require large order here. And the most important thing for the FIR filter, better than IIR is that the linear phase. So they can get linear phase. Last week I discussed very briefly what how to get. I mean, what's a linear phase? Why linear phase is important? And for the IIR, they also have a good thing. They normally IIR filter can just use fewer coefficients, and also nonlinear phase is not good, cannot control. And also the bad thing for the IIR filter, also a bad thing is like sometimes IIR filter, even you design a stable one, but because of the numerical error, and sometimes they can change to unstable filter. But for the FIR filter, they always stable. They never unstable because they don't have a feedback term. Do you remember we discussed, we just have a voting, like with the IIR or FIR. If it's IIR, they have a y k minus 1 or y k minus 2. That means in the feedback side. So here, if you look at IIR and IR and FIR, the structure. So the structure, this is a FIR. You can see only have one loop that feed forward. They don't have feedback. If you look at this is the IIR filter. They have feedback. So if you have feedback, they sometimes, if from negative feedback change to positive feedback, and then the system will be unstable. Or we can calculate the pole. If the pole location, because the digital system, you have pole. What's the poles and zeros? If you know the poles and zeros, and you can simply see the pole location, you can tell the system is stable or not. For the because for the FIR filter, what's the pole location? I will show you where's the pole location. For the IIR filter, where's the pole location? So the pole, if it's inside the circle, it will be stable or not. Normally, for a digital system, if its pole is inside the circle, it will be stable. But if it's outside the circle, will be unstable. So I discussed very quickly about the IIR and FIR filter. Basically, IIR filter have good things. You only need to design a very low order filter. But for the FIR, you need to do high order. But FIR can get linear phase. But IIR cannot get linear phase. So this is the main issue. And also IIR may be unstable. Maybe if you design not well, it will be unstable. Even you design it stable, but if the stability margin is not big enough, and then if you have a numerical, if you have numerical error, and then it would become unstable. Now we look at another vote. We look at before our discussion, I want to have another poll. So this is related with Z transform. So this is you can see this is a FIR or IIR filter. Actually, this is a IIR filter. So if it's IIR filter, we can build. If we want to determine the stability, we normally transfer to a Z form, and then we calculate the pole of the filter, and then we can determine stability. So the first step is to transfer the system in its Z transform. So there's a three answer. Can you try to select which one is correct? So you just I just before during a waiting time, I continue discuss about the continue discuss. I use MATLAB to show you what's a linear phase and a nonlinear phase. So this one is I first design a IIR filter. So IIR filter, if I run, so I run IIR filter. So last week I already show you this example. Actually, this where example is like there's a ECG signal is polluted by 50 Hz noise. So you can see this is not FFT. It's like a Fourier transform. So it's a little different with FFT. So Fourier transform we explained in the example. So here you can see there's a 50 Hz noise here. But after we use the IR filter, we can see whether we reject. So we reject it quite well. I mean, because the the blue one is quite a bit small. So that means after that we can get rid of. But there's a very bad thing is like they have distortion of the signal. And how to see the distortion? So this is the, for example, this is the magnitude response. Magnitude response, you know, we our passband is 45 is 40 or 45. I think like what's our design? Is it 40 or 45? So our cutoff frequency, so its cutoff frequency is 40. It's 40, and then our design is exactly 40. This is the low pass filter, and the cutoff frequency is 40. And we also have phase response. So you can see phase response. This one is nonlinear, right? Even in the passband, in the passband is 40 Hertz, right? So in the passband is still nonlinear, and in the stop band looks linear, but it's no use because we not use the nonlinear side. So that's why your group delay is very complex. Group delay, you cannot is not is a constant group delay. So it is not that good. So that's in the sense for the for the for the IR filter. And IR filter is sometimes we need to see whether it's stable or not. We can draw the plot of poles and zero. So you can all zero here. Zero is in the -1. Is in the -1, right? So they have 60 0. But the pole here, pole is very close in the unit circle. If it's touching the unit circle, it will be unstable. But this is not touch because if you look at any pole is not is inside should be inside the unit circle. But some of them is quite close. It's even you can see very close. If you have some little numerical disturbance, maybe make it unstable. For example, your parameter. That's why when do you remember last week when I show you the equivalent impulse response matching method, I use lots of digits. If the digits is not enough, it will influence stability. So although this one is stable because all inside the unit circle, but if I up disturbance, will not guarantee it. Now we look at the linear phase. So linear phase is quite good. Let we see the linear phase. So this is we designed the nonlinear phase filter, and then we design linear phase one. So linear phase one, we first use just low pass filter. We uncomment and then comment this one. So our polling is like the first one. Most students select the first one. So the Z transform actually is in the. So the first one is correct because the second one I deliberately make a mistake is like I put a positive one. So this actually should be negative one because you have time delay, one unit delay. So you need Z minus one. So the first one. So most students get the correct answer. That's very good. And based on that, we will discuss another one to determine stability. I will do the polling later. So you look at this is you can see we use a linear filter. So linear filter here you can see we see the phase. So the magnitude is similar as this, but you can see the magnitude, the linear phase has lots of ripple. Can you explain why they have lots of ripple? But for the IIR filter, not lots of ripple. And if this is magnitude response, so this is a phase response. So you can see in the passband, 50 hertz, 40 hertz, they are linear, totally linear. And but for the stop band, they are also linear, but they are not continuous. So the discontinuity is because of what? It's because of the zero. If the zero is in the unit circle, and then they will have ripple. If the zero in the unit circle, like stability is like if you have poles in the unit circle, will be boundary marginally stable. If outside the circle will be unstable, but if on the circle will be boundary unstable, boundary stable or unstable. But if the zero in the circle, in the unit circle doesn't influence the stability, but it will generate a ripple. The ripple is something like this because you can see if I write them together, draw them together, you can see the ripple is corresponding the generate the discontinuity because yes, if they here have a zero and then if we actually if you draw it's zero, so the infinite minus dB, right? Because zero is infinite. So in that case you have this one discontinuity and also you have ripple. So if you look at the pole and drawing, and then you can see the pole is the pole location is all in the zero. That means there we have 30 pole here. So this one that means zero is very stable, right? It's far from the unit circle, right? It's inside the unit circle and in the middle. So that means FIR filter never unstable. They always stable. And also you can see the zero, there's lots of zero. You can see the zero is inside, is on the unit circle. That means they can one will generate one ripple. So you can see the ripple, lots of ripple, right? And then you can see there's they also have the property for the zero. They are this one and this one, there's coupled. This one is inside and outside is always coupled. And then they are also conjugate. Here have zero, and then here also have zero. The symmetry with the real exercise, and also have a pair uh, inside and outside the unit circle. And the good thing is like always stable for the FIR filter. And also you can see they are very match quite good. but not perfect. If because this is not a notch filter, they damage a little bit signal in the 40 hertz, because you can see if we look at the low pass, you can see they are not very sharp. They also have some distortion, little distortion here, because you want to 40 hertz, they are not very level, very flat, right? They have some distortion. And then we design, maybe we design a notch filter. If we comment here, we put notch filter. So here is a band stop, or called notch filter. And then we look at want to see the linear phase, whether it's a linear phase or not. So it is also linear phase, and there's not many ripple. That's a good thing. So this is a notch filter, right? We only get rid of 50 hertz noise, and then we'll less damage the signal. So you can see this one is nearly exactly match with the original signal, and they have no damage, not much damage with you can see the inside signal nearly not changed. So this is the best one we need. So now we look at the spectrum analysis. For this is this is a magnitude. You can see 50 hertz, make it very low, minus 40 dB, and we have a linear phase. You can see this one is all continuous, no discontinuous. We can think like maybe there's no zero in the unit circle, on the unit circle, and we look at both phase and so you can see there's no ripple as well. So we look at the power and zero. You can see there's no power, no zero. Power is again is all in the very stable. It's in the zero, so it's far from the unit circle, and also it's inside the unit circle. It's very stable. You can never make it unstable. And then you can see all the pair zero is far from it's not close to the unit circle. Only one on this pair we can look at whether they are close or not, but actually they are not touching. They still have distance, so they are not touching. So that's why you see this one, there's no ripple. So yeah, that's when you write your report, you can do some analysis about maybe you use only low pass. Maybe you, for example, if you just EMG signal, maybe some EMG signal, the disturbance of 50 hertz maybe not that clear, or it's maybe not necessary. But if there's a 50 hertz noise you want to get rid of, maybe you can design the notch filter. So this is only the offline analysis. So online one, you need to maybe use live view. Last time I think Jeffy will have show you use live view, and we maybe Simulink. I use Simulink. Simulink is also quite similar with the live view, also graphical programming. So they can analyze, simulate the real-time signal, real-time system. Now we have another pole. So the another pole, another vote. Maybe we under this polling, So I think the 10 students select the right answer. That's quite good, quite impressive. The next one will be little hard. So the stability of filter. So here's the filter. I give you the filter here. You know how to calculate the pole and zero. You should know how to calculate. If you know how to calculate, and then you can determine if the zero, if the pole, we only look at the pole. If the pole is inside the unit circle, it will be stable. It's outside, it's unstable. So you can start to do the start to select is that stable or not. Yeah. Due to the time, I will do some other things. So we open the Simulink. So we look at real-time explanation. So here is in the real case, like real-time implementation means like you when you do the signal processing, you can only use the current available input and output. You cannot use the future input output. But for the offline analysis, you can use any output input you can use. But here is we simulate this one, and then this is the ECG signal, and then this is 50 Hertz noise. You can also put random noise in, and then here is a IIR low pass filter with low order. So we do the simulation. So you can see this one have a is actually get rid of some noise, but have delay, right? This is what we want to design. But if, for example, stability, now we look at the stability. Uh, if it's a, we change the value of the filter I input in the polling, in the voting system. We look at the polling. So most students think this is stable. So why it is stable? So because the pole is the pole is what's the pole value for this one? It's because it's 1 minus 0.25 z minus 1, right? So the pole is 0.25. So 0.25 is inside the unit circle, so it is stable. Yeah. So the most students get the right answer. I finished the polling, and we have a. So the last question is like linear phase. What's the condition of linear phase? So for this one, if we input the one, because the numerator is one, so this is So we look at this one is the one we designed the filter why it's stable, because if so this one is not very good, because in the sense 50 Hz still there, but it is stable, this stable one. But if we, that's why the system is stable. But if we change it unstable, put an unstable one, that means, for example, we put this one is 1.25, and then this one will be unstable. They'll go very big, go to very big, because the time simulation is not long enough. Maybe still not that big, but so you can see this one is go infinite. You can see this one go to infinite because of unstable. They go to infinite. So this is a example. We can make it back. Yeah. And the next topic is very important topic is linear phase. So you get linear phase is not free. It's not like you can get linear free, freely. We look at what we designed, why we get linear phase. We look at the coefficient. Because for this one, this one is linear phase, right? So we look at so our linear, this one is the coefficient of numerator is nn. If nn, we cannot see the whether what's the structure. But if we plot nn to have a look, so you can see that's the coefficient looks like, because they have the order is 80, so they have 80 coefficient. But you can see this one is a symmetry. So the coefficient is symmetry. If the coefficient is symmetry, and then they can get linear phase. This is the one example. This is a notch filter. Remember, the notch filter looks like the coefficient. If we change to other filter, for example, we go to IIR filter, and if go to another FIR filter here, if we sorry, we should stop. This one is still, don't worry, this is a wrong one, so we not comment here, so we need to, but anyway, for this one you can see you get maybe I close this one, so this still the notch filter, so the coefficient is still symmetry. So I tell you the condition to get the linear phase is like the coefficients should be either even symmetry or order symmetry, or called anti-symmetry. If this condition satisfied, they will get linear phase. We look at this is a if we look at this another linear phase one, if we run, we will discuss later. But first we go to the reading material. I put here. So here discuss what's the requirements of linear phase to get a linear phase. So they called linear phase if symmetry. This one is if you draw the figure, this is a symmetry. Get, and I think there's one video discuss very clearly about how to design linear phase filter.
An important property of FIR filters is that they can be designed to achieve exact linear phase. We're going to look at what that means for the FIR filter in this particular lecture. Recall that the frequency response of an FIR filter can be expressed as a weighted sum of the filter coefficients. So here we have the sum of the BKs, e to the minus jk omega, and over 2, and that falls
you
on
can
an
have a four
index
type of
because m is
symmetry
an even number,
thing.
and so this particular
So they have four kind of scenario. So because you have m is the, for example, is the atoms, it's the order plus one is the m. So in that case, if m is even and you even symmetry is one kind of linear phase filter, you can also have other type. But the most useful one is symmetry. Anti-symmetry actually is not that useful. So it's a symmetry one we'll discuss here, give you the lots of condition, lots of discussion about even about four cases. Basically, you can check here. This gives some limitation for the design the linear phase. Here is the one is useful for you if you get rid of
We would like to filter out
50 Hertz noise. How to use MATLAB to design the stop band filter. And they have discussed the how to find the Nyquist sampling frequency. So it's you need to normalize your frequency in the with the Nyquist sampling frequency. So it's related with your sampling frequency. So these two video is quite useful as well. Now we look at our result for the. So this is a low pass linear phase filter, and we look at the the coefficients. I think the coefficients is also even symmetry because normally they divide even symmetry. So this is the numerator coefficient. If I draw this one, this is also can guarantee this also even symmetry. Sorry, even symmetry. They are symmetry. So they are. This is 32. What is 30? 31 because they start from 1 here, so you should start from 0 and then it's 30, so the order is 30. So this is symmetry, so you can see this is symmetry, others are all symmetry. So this is a linear phase. We look at if we look at a nonlinear phase 1 is the comment. If we look at this is IIR filter, we know it's on it's not linear phase. We look at what the coefficient looks like. But anyway, so this is the condition. Now we look at another. I look at another final pole. We look at the linear phase one. So can you tell me, is this one is a linear phase or not? Is it yes or no? So here we look at this is the IR filter. IR filter, you know, is not a linear phase. You look at this one is nonlinear. It's even in the passband, it's nonlinear. So we look at their. If we look at the NN, this is the numerator. If we look at this one, we plot. We can see this is maybe is not a linear phase, but looks something like a linear phase. This is what's the one we use. But because they have a denominator as well, so this is only numerator. We look at the denominator. So it's so that they have denominator. So there looks also symmetry, but they are even is not in the because they have feedback. They even satisfy the symmetry requirement. They are still not linear phase. So we look at our voting result. So we have 8 students say this is a linear phase, and 4 students think it's nonlinear phase. So this I left you as homework. I think this one is very tricky, and I will discuss with you in the future lecture. And this is all the things I think linear phase people. So this is for the lecture for today, and I also want to spend a little time to discuss about because we will have a long holiday. We have 2 weeks. Although you will do the assignment 1, but I still put some reading material after you finish your assignment 1. We will discuss about very important content. It's called short-term Fourier transform. Actually, we start to consider about non-stationary signal. So for the second stage, although I mean the procedure is similar with the first stage, but the report will be individual report, not individual. It's still group, but we will mark. You need to mark which part is which you get, which member write this part. So that's little tough, and but the overall the requirements is similar with the stage 1. So now I go to the canvas. Actually, I haven't published uh, the I haven't published the lecture 4 yet, week for lecture 4 yet. Although we called week 4, but sometimes it's actually it's a little delayed because sometimes I will adjust the progress. And so this is just like you don't be too serious with the week. But this I will put some lecture notes here to discuss what's the short-term Fourier transform. I tell you why we need to discuss about non-stationary signal. So how do you design a filter to cope with? Because non-stationary signal for biomedical signal is very common. For example, we have EEG, ECG, EMG. Because you know, like when you want to determine, unless the person is in the rest or sleep or something, or this in the very peaceful state, and then maybe EEG, ECG, EMG is non-stationary. It's stationary, but when some stimuli happen, for example, if someone running for a while, and then the ECG will change, so will maybe gradually the frequency will increase, mean that heart rate increase, and also for the EEG, you know, like if you have different brain activity, the frequency will also change. EMG, when you do some maybe EMG, the frequency not change much, but the envelope will change. But in that case, mainly for ECG and EMG, EEG, there will be a non-stationary signal. So in that case, if you still use the FFT to analyze, you cannot see the change of the frequency. So that's the main problem. So in that case, next stage, there's lots of scientists want to improve to directly improve from FFT to deal with non-stationary signal. So there's one very powerful tool. It's called short-term Fourier transform. That means they put a window. That means the window is moving, and then because we can make the window shorter, and then we can pick up, for example, if a rectangular window, we only pick up a piece of data, and then we do FFT, and then we can, when the window moves, we can see the frequency change, and then you can see even not use a rectangular window, you can use other window, make it result is more beautiful. You also have a shorter Fourier transform and also have inverse short-term Fourier transform. You can recover the signal. So next to our stage 2, we will discuss how to use MATLAB or LabVIEW or even Python to design a short-term Fourier transform to analyze the signal. And later on, we will discuss another very important problem is tools called wavelet. Wavelet, we will discuss both analog wavelet, continuous wavelet, and discrete time wavelet, DWT and CWT. That was a big project, a big topic. I will put some reading material during your holiday. Yeah. Maybe that's all for today's